Good evening, everyone. So I would like to warmly welcome all of you to the fourth session of SparkLink on behalf of the IEEE Student Branch of the University of Ruhuna. So SparkLink is a series of 5 sessions, and today marks the beginning of our second phase. So today's session is going to be about an introduction to HDL, which is a specialized programming language, and it's going to be used in the field of digital electronics and integrated circuit design. So it's a pleasure to see all of your continued participation and enthusiasm. So there's a large number of students in the crowd today, and we hope you will be with us for the rest of the sessions as well. So just like our previous sessions, today's session will have our guest speaker, who is going to conduct the session for 1 hour. And afterwards, there is going to be a short 10-minute quiz to take your attendance. So the attendance is going to make you eligible for the e-certificate that we will be providing. So please make sure to join in for that as well. Now, let's move on to the most awaited part of today's session. Today's guest speaker is Mr. Ruchir Pereira, who is an application engineer at Synopsys. He's also a graduate of the Faculty of Engineering, University of Ruhuna. He's an expert in the field of electronics and highly skilled in electronic circuit design and simulation. And it's a pleasure for us to have him here today. Dear sir, now the virtual stage is open for you.
Okay, thank you. Can you all see me and can you all hear me?
Yes, sir.
Okay, give me a second. I will start sharing my screen. Okay, I hope you can see my screen.
Yes, sir.
Okay, so let's get started. So I'm going to do a small introduction session on Verilog and HDL and how this thing helped in our lives and how these things are important to us. So let's get started. So this is the outline that I'm going to cover today. Introduction to HDL. HDL means hardware description language. So I will come to this point a little bit later. So I will describe how this thing helps us. And the first thing I'm going to cover is introduction to EDA. Actually, EDA stands for Electronic Design Automation. And introduction to HDL. Actually, HDL comes under EDA. So that is why I have included this one. And under HDL, we have Verilog. And I'm going to do a small introduction to Verilog. And then we will do simple module writings in Verilog. And also we will do some simulation using online platforms. So first thing, while I am doing this session, please try to go to edaplayground.com and try to log in with a Gmail account or any other account that you can provide and try to like prepare the setup for us to do some simulations later. Okay, please try to go to edaplayground.com. Okay. And what is EDA? So anyone has any idea about EDA? You can raise your hand or just give an answer on the chat box. Any idea about EDA? Electronic Design Automation. And by the way, who are the students we have here? It is batch 22. Is it?
Yes, so we have students from the 22nd, 23rd, 24th as well.
What is the latest one?
The latest batch is the 24th. That's
24. Oh, good.
Yeah.
Okay, so major is 24, right?
The 24th lecture just came a few months ago.
Okay, okay. So, do you have any idea of electronic design automation? Have you ever heard of this term, electronic design automation? Have you done anything similar to this field, like doing a PCB design or something like that? It is also even categorized under electronic design automation. So, has anyone heard of this? At least one hand? No one, right? Okay, I will play this video later. Here's a video, and I will do a small example for you. So before come to electronic design automation, have you heard about this term automation? So what does it mean? So I'm going to skip to the next slide. So this one, can you identify the difference between the first picture and the second one? So the first one, uh, there are some people assembling a car. It should be a brand new car, and you can see the practice outline. Uh, you can see a few people around the car. They are assembling the car. So in the second part, what can you see? Can you see a human on the second lineup? No, you can't see any human, right? So basically that we can assume no human is involved in the second process. It looks like a painting booth or something like that, but however, no humans are involved, and everything is done by robots or robo arms. So however, the process is automated, right? So this is the typical automation. So why do we need automation? As engineers, we have to know this thing, right? Why are we moving towards automation rather than doing it manually by humans? So the first thing is we need to reduce the cost of labor. So the first one, maintaining humans as laborers, it is highly costly. So people are moving towards technology for that one. And the second one, accuracy. So this thing done by human, and when it compares to the things done by robotic hands, so robotic hands uh, tends toward more accuracy. And the third one is speed. So we can maintain a particular speed throughout the process if we have this process automated by robots. And if humans are involved, the speed may vary. It can get to a good point, and it can get slower. It may vary. So we can't predict the output of the process if we haven't automated this one. And how this automation thing uh, is going to connect with the subject that we are going to learn today. So now I'm coming to this slide again. Now this is electronic design automation, and why we have automated platform in electronic design. So, and I'm going to give you another example. We all have mobile phones, we all have smartphones, and we use our smartphone for different things, right? And we do watch Facebook videos while we are listening to music, and we do a lot of stuff. We do a lot of multitaskings nowadays using smartphones, and we do a lot of things. We share a lot of things, and like smartphones have now become even more powerful than computers like 5-6 years ago, right? You guys agree? So um, why this smartphone industry or this computer industry need automation? Can you believe um, if you have a mobile phone this year? So I'm going to buy a latest Apple mobile this year, and within 1 year period, Apple is going to introduce their next phone, right? You guys agree? It is your mobile phone is just brand new, right? Whatever the current version, maybe you are buying a 14 today, and 5-6 months later, the Apple is going to introduce their next phone, and you are going to be frustrated. Oh, my phone is now no longer a brand new one. or it is not a new model, right? So how do they design phones in such a hurry? How do they do this thing in this quick? Have you ever think like that? How do they do this thing? So you all have heard that transistors and all the computer generations, right? The first computer generation that we know is vacuum tubes, and then comes the transistor, and then comes integrated circuits, and then microprocessors likewise. So now currently we are in the microchips and microprocessors stage. And do you know that inside the modern microprocessor, let's compare it with the Intel Core i7. So in that computer chip, do you believe that there are couple billion transistors in that one? So basically a transistor is a electronic device with two PN junctions, right? So do you believe that this small chip, the chip size is like 3 by 3 centimeters, and this small chip contains a couple billion transistors? Can you believe? So how do they have integrated this circuit into this small piece? And that is the question, and that is how this electronic design automation thing comes into the picture. And basically what happens is, inside electronic design automation, we don't do anything, by meaning of anything, I mean like we don't do any like calculations or any designing part, anything by our hand. So we think about the logic that our chip needs to do, and then we code it. With a certain language, and then the computer is going to do the rest for ourselves. Okay, that means we don't do anything, like we don't you, or if you have ever designed a PCB, then whatever you do, you will have to first finalize the schematic diagram. Then you will have to lay out all the components depending on various factors, and then you will have to do the fabrication or the manufacturing portion. And in this way, you don't do like that. So first, what you have to do is you have to think of the complete logic. You are going to finalize the complete logic, and then you will try to do a simulation in a computer aided design environment. So that means a CAD environment. And once you have finalized your simulation, then you will be able to do the layouting process even with a computer help. So nothing is nothing is manual. Everything is automated. That is how this electronic design automation comes into picture, and that is why we learn Verilog. So basically, Verilog is a very popular language that we can do electronic design automation. And now I will try to play this video. Not sure you will see it very clear. Let's see. Okay. I got a message saying that you cannot hear the sound. I'm not sure why. So, however, I have shared my environment with sounds. Okay. Just give me a second.
All this and more.
Now can you
Architectural
hear the sound?
analysis, simulation, verification, physical design, manufacturing, semiconductor IP, and application software development are all enabled by EDA. Electronic design automation is at the heart of today and tomorrow's innovations, and without it, our world would be far different. Did you know Synopsys is a design?
I'm going to play it from the beginning again.
Electronic Design Automation, or EDA, is a collection of hardware, software, and services aimed at one goal: the design and manufacture of advanced semiconductors that are impossible to make without it. The EDA industry began over 40 years ago. Since then, EDA has delivered about a 10 million-fold increase in design productivity. And with the current prevalent use of semiconductors for things like AI, fully autonomous cars, IoT, and more, EDA must deliver more productivity than ever before. Today's advanced semiconductors contain multiple chips and technologies, with billions of transistors all packed in an ultra-small form factor. And all of it must work flawlessly, meeting demanding power and performance goals on tight schedules. There is no way to do this without the sophisticated hardware, software, and support EDA provides to design and manufacturing teams, so they can predict and optimize performance and better ensure a manufacturable result. There is also a pressing need for pre-verified building blocks to reduce design time. EDA delivers all this and more. Architectural analysis, simulation, verification, physical design, manufacturing, semiconductor IP, and application software development are all enabled by EDA. Electronic design automation is at the heart of today and tomorrow's innovations, and without it, our world would be far different. Did you know Synopsys is at the forefront?
Okay. Yes. So, what are the key points that you have taken from this video? What did you see in the video? So, if you are like a first year student or second year student, you might know some of the things that we have just discussed, but don't worry. Okay. So, this is a completely new area that you will not very easily find in your university life. So, I'm just giving the introduction, so you don't need to worry about like this thing is completely new or you don't understand anything. Just hang in there, okay? We will try to do some examples at the end of the session, and you will get some idea. So just don't worry until then, okay? And did you see that? Have you ever heard of the Moore's law? Even in A-level ITs, the Moore's law is being taught. Have you seen Moore's law in the video? So basically, Moore's law states that the number of transistors in a electronic circuit doubles every I don't know, every 2 year, 3 year, or there's a so however the meaning is or the thing that Moore's law says is we are getting our lives even more complex than today. Okay, so for facilitate that complex life, the electronic industry is going to be even more complex than today. Okay, for that purpose, the electronic manufacturers and all other related parties, they are trying their best to improve this technology, improve everything, improve the heat dissipation, improve the battery capacities. Likewise, everything they are trying to improve. That is how the technology improves, right? So basically, if we are going to look at a mobile phone 10 years ago and a mobile phone right now, what do you see? So 10 years ago, mobile phone will last longer, right? So battery capacity will last longer if it is a normal mobile phone, if it is not a smartphone. But from all other aspects, so we have a camera right now, and we can just share a picture within seconds. We are connected to internet very easily. So we didn't had any internet facilities like 10 years or 20 years time. Likewise, so we have improved a lot in the electronic industry. Okay, even next year mobile phone will be even full with new features. So that is how electronic design automation comes into picture. And do we have any questions up to now? I saw one question. Do these repetitive tasks move past? I'm not sure from which point you are asking. Can you better if you can unmute your microphone and ask the question. And if you can't, it is okay. You can type it in chat box. So the language doesn't matter. Okay, you can ask your question in any language, Sinhala or English. Don't ask in Tamil. I don't understand Tamil. Okay, so you can ask any question. If you need to ask any question, just raise hand or send it to chat box. Okay, do you understand what I just said up to this point? Anyone? At least a moderator or the organizing committee? Oh, okay, sure. Okay. So basically, that was not a question. It was answer. Okay, yeah, your answer is correct. Yes. So basically, the summary is we don't do electronic designs by manually by ourselves. So whatever we need to design, we are going to finalize our logics only, and then we are going to feed our logics into a certain program or a set of programs. Then the computer or the programs will do the rest for ourselves. So it will basically take our design, basically our idea, and then they will simulate. They will do all the safety checkings, and they will do all the layouts, and then they will do everything from our point of the design to the fabrication level. So basically everything will be done by computers, so that will save a lot of time. So if you are going to if you have done any kind of simple project in your university life, let's say if you are a third year student, and have you done there were a few projects in our time, electronic design or something, and also in one module there was a filter project. If you have done any kind of project, then you know how difficult it is to do the simulation and do the finalizing the schematic. And even though you have finalized your schematic and everything works fine in the simulation, and it is that difficult to get it in onto a real board. So making the PCBs harder, and getting everything on the board. And once you have done everything and your board suddenly drops on the floor and everything is done likewise. So you know how hard it is to get even a simple circuit, and that circuit might contain like 20 transistors. And can you believe how hard it is to uh, design and build a circuit by ourselves if the circuit complexity is like 18 billion transistors? So it is very difficult, right? So that is how the electronic design automation comes. Okay, this is what I just explained, and this is a small schematic diagram of a particular ASIC. In this slide, you will find a new term, ASIC. ASIC stands for Application Specific Integrated Circuits. So that means a IC that is developed for a particular task. So if you have any experience with ICs, op-amp is kind of a ASIC, and even a good example. So have you ever heard the nitride circuit? Have you ever seen a nitride circuit built with CD4017 IC? So that is a ASIC, that is a decimal counter IC, and you are using the decimal counter IC to light 10 LEDs in the pattern of nitride. So you know nitride, right? Nitride ka. So that is one application specific IC. And likewise, this is a small logic diagram or the schematic diagram of that IC, not that one. It's a particular IC. So I just want to give you the term ASIC here. Okay. because this will be useful. And again, one of my questions, have you ever programmed an Arduino? Have you ever tried to program a microcontroller? Arduino is a basically Arduino is a platform that made easy to program microcontrollers. Even in this board, you will see a long IC that is a microcontroller. Actually, a 80 mega 328 PPU is the brain here. This is the microcontroller here. So this is a easy platform that you can make circuits or make systems, make embedded system very easily. Have you ever programmed Arduino? You may have, or sometimes you haven't, or sometimes this is the first time you are seeing this board. Okay, doesn't matter. However, the thing is, you can connect this board to your computer using a USB cable and using some IDE or a software. You can program this one. It is very easy. If you have never tried this one, try to get this board, and it will not be that expensive. So I don't know, from our times it was like 1,000 rupees. I don't know the current price right now, maybe 3,000 rupees likewise. So try to at least do something using this board. It is very interesting, and uh, you can learn a lot from these boards, from about digital electronics and also analog electronics. Okay, so if you have ever programmed Arduino, you will see that you can use this IC's memory, and you can do some programming, and that program will run inside this Arduino board once you have powered it. But let's say this is I am explaining this to the people that who have that you have experience with Arduino. Okay, if you have like coded an AND gate inside the Arduino, and have you tried to make the process, or have you tried to experience the process of the AND gate while the microcontroller is turned off? I mean, when we have not provided any power to this computer or this microcontroller, this AND gate function that we have write is no longer valid. Okay, basically what happens is when we have provided power to this board, it will load their program, it will come to life, and it will load the program, and then it will act as the AND gate. That is how the IC works. But when it comes to the language that we are going to learn today, it's working a complete different manner. Okay. Yes, another example that I needed to show you. Can see this is a list of current processors that we have in the market, and can you see the transistor count? Actually, this slide has to be before the last one I have explained. Can you see the transistor count and the area? And in this one, AMD Genio IC, the transistor count and the area. And this the last one, Sapphire Rapids. So this is coming from Intel. Can you see the transistor count and the area? So if you have seen this area number, so you will be amazed. Okay, it's a very powerful processor, and it's a very small area, square millimeters. Okay, this is kind of a this is the kind of density that we are working on right now, and this is Moore's law. Okay, and of course these parts I'm going to explain is more of a theoretical part, but we have some practical works in the next few slides. Don't worry. Okay, so I have to explain these parts, so otherwise it will not make any sense. This is Moore's law, and so it says that you can see it. Number of transistors in an integrated circuit doubles every 2 years. Okay, and the time period is 2. So you can see the graph starts from 1970 and it continues to 2020, and the transistor count so almost doubled, right? So you can see that how this straight line is going up. Okay, this is most low, and to keep aligned with this most low technology, and all the teams, all the electronic manufacturers, and all the EDA technology manufacturers, software developing people, everyone is working hard to keep this in line. So this is how the most low going forward. Okay, now coming to our main topic, HDL, a hardware description language. So basically, what uh, if you have heard of any other language, any computer language, C, C Sharp, or Java, something like that. So you might think HDL is also kind of program like that, but it is completely different. So basically, HDL languages are used to describe electronic circuit. Okay, basically it is electronic circuit. It might be digital, it might be analog. Basically, we say it as digital circuits. But however, HDL, when it comes to Verilog or system Verilog or any other HDL, it is basically describing a language or a digital circuit. Okay, so it is not a regular programming language that we use. So you can see on the left hand side, there's a small code snippet, module and gate. So this is the module keyword is there. I'm talking about this one. And the end module command is there. So basically these are two keywords. And in between these two keywords, you can see the module name. So this is a little bit of I don't know. If you have some programming knowledge, this will be very easy. So you know the exact format. But if you don't have any knowledge, but don't worry. So it is very easy. Okay, so you can very easily identify what are the things. You can just go through. There's a chat message. Could you share the slides with that? Of course, I'm going to share the slide. At the end of the session, I will share the slides with the OC, and they will share it with you. Okay. All right. So now coming back to the point, this is the module definition, and the second one is module name. Even these are named in a future slide. Okay. And then we have in parentheses we have output O. That means we have defining output. We are defining an input. Sorry, two inputs, and then within this body we are going to assign O equals A and B. So that means we are going to make a AND gate using a small code decimal. So do you understand what I was saying here? So basically this code decimal explains a electronic circuit. This is the electronic circuit. So basically it is describing a AND gate. And now by using this AND gate, I'm not going to draw, or I'm not going to like place a AND gate manually in any circuits. I'm going to just define my AND gate like this, and the computer will do the rest for myself. Okay, so that is the idea of HDL. And this is basically Verilog. Okay, I have used Verilog for this code, and I will show you how to write this module. So this is a basic code snippet and how it works. Okay, and the types of or the HDLs, hardware description languages. We have Verilog. It is very popular, and we have system Verilog. A little bit towards Verilog, but it is some keywords are different in system Verilog. We have VHDL. Actually, I think VHDL is the older one, which is not very common these days, but still in electronic design automation, VHDL are using. System C is the newer one. Most of the software support it, but I don't see major support for system C right now. The major support is for Verilog. Okay, so if you can learn Verilog, then you will see a lot of simulators online. Okay, Verilog, I'm going to do a little bit teaching session on Verilog only. Okay, so Verilog is the standardized IEEE language. So basically, Verilog was developed by different companies, and then IEEE made it standardized, so it will be used among many electronic design teams and manufacturers. Sorry. Okay, field programmable gate arrays. I will come to this a little bit later. Okay, I will just skip to Verilog code. Right. So this is the one I need to spend a lot of time. This is a part of a Verilog code. So we are going to write an AND gate today. So basically, we are going to do a small introduction to Verilog, and then we are going to do the AND gate. We are going to implement AND gate using Verilog, and then we will try to simulate it. So basically, these are the identifiers, or this is how we identify this code. This is the module keyword and the end module keyword. The module name here, port declarations. That means all the ports that we are going to use within our module, we need to describe them here. And I need output port, input port, two input ports, and then the function in the body. Okay. Now, once I have write this code, and now I have wrote this one, but this doesn't mean that I have an AND gate now, but it is not my circuit. Okay, I need to build my circuit, but AND gate is a basic element in there. Then we are going to open a new module, and this is just test bench. Okay, I will explain what is a test bench later. So in this module, you can see there are no ports declared. Okay, you can see some reg type variable x and y and a wire type variable z. Okay, these are two types of variable. I will explain them later. And in this one, if you have any programming language knowledge, you will see that this is an instance creation. And basically what it does is it creates a AND one instance of AND gate that we just created. What happens is this is just the template that we are going to use. This is the template. And here we are going to create instances by using that template. That means if you need to let's say you need 6 AND gates in your design, then you don't need to declare this module again for 6 times. Okay, you can just explain this module once in your program, and then you can create whatever the number of instances you need. You can create the second one like AND gate and 2, and then you can open and close all these parentheses by providing the particular registers or wires. And now I will come to these two registers and wires. You can see now when I have created this instance, you have we are trying to access this O. What is this symbol O? So we don't have any simple laws in this scope. We have a simple law in this scope. Okay, in this AND gate. Okay, this O refers to the output of that particular AND gate. And what we are going to do is we are going to create this AND one instance here, and we are going to refer this AND one, and we are going to try to connect our variable or this wire type to the output of that AND gate. Do we agree to what I'm saying? If you couldn't follow up with me, just put a message. Or if you can agree or you do understand what I am saying, then please tell me. Okay, basically what happens is we have created our AND gate template here, and now I am going to use multiple AND gates here by using these declarations. If I need to create a second AND gate, then I will follow the same format: AND gate and 2, and then within these ports, I need to for this one I just need to create my output to output to the output of this module. I will show you the example. So this is the one I am trying to do right now. So this is basically my Verilog code or my AND gate, and this is the test bench that I just showed you, the test bench code. And what I am doing is I am creating this AND gate circuit in my software or my coding, and I am also creating this test bench. And now I need to connect my test bench X wire to this A port of this AND gate, and this Y wire to my B port of this AND gate, and my O to the output or this Z. Okay, that is what I am doing here. Okay, we will just go to the code, so it will be very easy. Can you try to go to this website? It is edaplayground.com. So I know I am rushing through the contents, but we have to stick to the time frame, and there's a lot to explain. And without explaining what is EDA and things like that, you will not get any idea. Okay, that is why I am trying to cover everything. Okay, if you have the interface like this, then you can just follow me. I will start doing. So the first thing you need to make sure is from this test bench plus design, try system verilog /verilog or /verilog. So we will be using verilog. So basically, this is the default action. If you don't need to change, don't change it. And you see that there are some other VHDL as well. And UVM, OVM, you don't need to use UVM. UVM stands for Universal Verification Method. Leave it there. Let's leave it none. Tools and simulators, please select. So you can see multiple license commercial simulators. You can see Rivera. Is the name correct? Rivera, yeah. Cadence, Mentor, Questa, and Synopsys. This is my company, Synopsys VCS 2109. So I have the license for this one, but I am going to use this one. This is a free simulator. Yes. I am going to use Icarus Verilog 0.9.7. This is the simulator that I am going to use. So if you don't, even though you don't understand anything, just try to do this code with me, and then you will try to get some idea. Okay, the first thing, there are two tabs open for us. The first one is testbench.sv. SV stands for system verilog. I'm not going to change anything. And the second one is design.sv, that is design file. Okay, now I am going to write my design file here. I hope everyone can see my screen. Module and gate. Output O. Basically the same program that I have just showed you. Okay, in the okay, module and module keywords are there. Now I need to write my body here. I'm just trying to assign O equals A and B. What I'm trying to do is, if I have received any input from A and B, I am going to do the AND operation. This is AND operation of these two inputs, and then going to assign it to O. This is how basic program works. Okay. And in the test bench.sv file, I'm going to again write my test bench. Basically, we have our DUT or the device that we are going to test here. device under test here. This is my device, and I am going to create a test bench. You know what is a test bench, right? So basically, we are a system that we are going to test using some kind of inputs given to our system. Then that is the test bench. We are going to provide some inputs to our design or the device that is basically AND gate, and then we will see what is the output. Okay, this is the test bench that I am going to write. Basically, you can use any name, but I am going to use TB here. And if you remember, I was using two variables x, y, and also one wire type variable. And if you remember, I was having a instance creation, and I'm going to do that. And gate, basically this name coming from this module. If you have defined a OR gate here, like module OR gate, then the same pattern. If you need to create a OR gate here, then you will have to use OR gate. Okay, basically whatever the name you have provided here. And gate and one. And please note this notation. So basically this is a way that we are going to call our inputs and outputs. So this is how we connect them. So I'm going to connect my AND gate O output to my Z. That means this wire. Okay. And the same A input to my X register. Reg stands for register. And my B, my B to Y register. That is right. Okay. And before I forget, we will write this end module command also. And now I will do some test benching here. So up to now I have defined my AND gate and my test bench, and I have created some registers. Or basically we are using registers to provide inputs to any kind of design that we are going to make, and we are using wires or wire type variables. So can you hear me? Okay, I hope you can hear me. I was just disconnected. We are using wire types to connect in between circuits, right? Okay, now I have created my instance here, and now I am going to introduce my test bench. Okay, up to now I have not given any input. You see, we have AND gate. We have not provided any input. X0, 1, Y1. Likewise, we have not provided any input. So now I am going to do that one. Initial, begin, and end. So basically, I am trying to use this initial block. So one thing I need to emphasize is these initial blocks, they run from the start of the simulation, and they run only once. Okay, this initial block, it will run only once, and there is another kind of block that is always. So it is also introduced in the same manner, just the name differs. Always an initial. This initial block, it will start from the beginning of the simulation, and it will only run at the initial or the beginning. This always block, it will run every time. So we need to provide something else also here. It will run always. Basically, it will run at every time. And there's one different I forgot to mention between Verilog and Arduino. Okay, so when we have created something from Verilog, or when we have created a large design in Verilog, so basically it is finally at the end of the design, it will be fabricated into a IC or a chip. Okay, so that means we don't have any software control inside that chip. It will basically run as a piece of silicon. Okay, so if we have created this AND gate inside the design, so it will basically come as a AND gate. It will be physically a AND gate. So what happens if you have programmed this thing into Arduino? So it is not going to be an AND gate. Basically, the IC is turning on, and then it will act as a AND gate. But in this case, it will be physically an AND gate. Okay, because of that thing, we can do parallel processing inside Verilog or inside the chips. So because it is being physically fabricated to a system. So because of that, we can use multiple blocks here, even though you have created several initial blocks here. If they are synthesizable, there's a term called synthesizable, so you will learn them in the future. If they are synthesizable, then all these things will comes to your chip, and every of them will work in parallel manner. And one another point I need to emphasize. So this is basically our design, right? This is our design. This is the circuit that I am going to make, and this is just the test bench I am going to make just to verify or to check my circuit is working fine or not. This is my circuit. Okay, AND gate is my circuit, and this is the test bench I am going to write just to verify my AND gate is working fine or not. Okay, so this part doesn't need to be in the final production or the final chip. This is just the test bench that we are going to use. Okay, just forget about this part. I'm going to write the test bench here. X equals 0, y equals 0. So even though you don't understand anything up to now, still you have a chance. X equals 0. I'm going to basically write uh, all the combination that we can find to feed this circuit. I'm just to give a explanation on this hash symbol. This is used to provide time units. Okay, that means initially the value is x0, y0, but after one time unit, the value should be x0, sorry, y1. Okay, now x1, y0. Okay, good. This is our basic circuit. And now I am going to use one always block as well. So this is to just show you how the simulation work. And I'm going to define my always block like this. It is always, and then we have at symbol, and then within parentheses we have this star symbol or the multiplication symbol. That means this line is telling to the simulator we are going to uh, change this event every time. Basically this will run every time. You can provide some logics here. If that is true, then this will run, but I am going to provide this wildcard in Verilog. So basically it tells the simulator it is running always. Okay, I can zoom in. And inside this always block, I'm going to use this Verilog system task call. I'm sorry, I know this is very complex, but try to do it, and try to then understand it. It is very easy actually. Okay, I think I have given all the necessary things. Let's try to run this thing. You can run this simulation on this top run button. Let's try to run it. Okay, so very good. So from the first try, it is giving some simulation outputs. Can you see 0, 0, 0? That means the initial value, and then 0, 1, and then y is 0. The output is 0, 1, 0. That means x equals 1, or a equals 1, y equals 1, and then output is 0. Here 1, 1, 0 and 1, 1, 1. So what happens here? 1, 1 still in 0. Okay, so this is basically how our circuit behaves at these given points, and you will see that there will be a question about this part 1, 1, 0, but 1, 1, 1. So I'm going to give some time for you at the end of the session, or whenever you have some time. Think about why this is 0 and why this is 1 here. Okay, why these display points have not come exactly that as we expected. So there's a logical explanation for this one. Okay, this is how our circuit behaves. Basically, I have created an gate. This is my circuit, and I have created this test bench, and this is my test bench. And once I have provided my test bench to this circuit, and I display my contents, so it will behave like this. And in this IDEA Playground website, we have this EP wave functionality, or this facility. We can use waveforms in order to identify or understand our code or our circuits. So I'm going to use that one as well. So I'm going to use a new initial begin part again. I'm going to basically use another initial block, and I will use this system task called dump file. So basically what happens is there's a file dump, or there's a file saved at the end of the simulation. So this one will begin at the beginning of the simulation. It will create this dump file. Sorry. Okay. And even though I have used this dump file command, it is not dumped until we call this point, this system task call dump was. So we need to call both of these. So basically it will dump.vcd file in the first one. We are just saying the name, and this system task call we actually says to dump it. So basically to save it. Okay. And also I'm going to tick this EP wave option here, and now I'm trying to run again. Basically it will recompile and do the simulation once again. See, there will be a new window open, and now you can see some waveforms, right? X waveform variation, Y waveform variation, and this Z waveform variation. So if you need to, so you can see, right, Z have not become one even at this point. So if you need to go even beyond this point, you can modify your test bench. You can add another 1, 1 block here, or 1, 1 point here, and it will go beyond this line. Okay, so we have gone beyond that line. Now we can see that Z has become 1. Okay, so this is how you write a basic Verilog code and a basic test bench. Any question? I know you will have a lot of questions here, but just going to ask from the organizing committee, do we have some time to do one more example, or do we need to stop right here?
No, sir. You can continue.
Okay. So if you don't mind, then I will give you one example to write. So basically, this is what we wrote just now. And how many of you have got this one working? Yeah, someone raised hand. If you have any question. SLW453. What is your name? I don't know your name. It's appearing like this. I think you are raising hand because you have got this right? Okay, yeah. So at least one person is going in the correct way. Anyone else who has got this working? Yeah, we have a couple. Yeah. Good to know. Yeah, we have a couple. So, so at least yeah, after this session, you will have some resource person inside the faculty, so that you can discuss and you can discuss and get these things working, right? So that is my hope. Even we have 2-3 people, that will be enough. Then we can share our knowledge, right? Okay, this is the task that we just did. We wrote a basic, very simple AND gate. Actually, this is one way of writing the AND gate. There are some other ways. They have some names. Just try to Google it. You will find a lot of answers. So Verilog, it is very it is not a very hard language. A lot of resources are available on the internet. You can find a lot of things. And you can use this open source simulator EDA playground to simulate it. And now I'm going to give you a task, and I'm not going to do this one. Okay, you have to do it all by yourself, and I will hope at least one person will share their screen and show that this is working. Okay, so this is the challenge. You have 2 AND gates and 3 inputs, A, B, and C. A, B are connected to through an AND gate, and then that's output will be fed to another AND gate. So basically, the output should be coming from all these A, B, C outputs, and this is the test bench that you need to provide. 0, 0, 0, 0, 0, 1. Likewise, you have to provide this test bench, and this is our test bench. And it's very similar to the circuit that we just wrote. You can you can create one AND gate, and inside the test bench, you can create multiple instances. Okay, you can create 2 instances, N1 and N2, and then connect to each other. Okay, what you need to do is you will need to create a variable wire here. Let me. So this variable will be a rect type register. So I explain you, we are using rect to basically get the inputs, and then we can use wire for intermediate connections. Oh no, this is not a wire. I'm going to leave it like this. This is the wire. Do we have this? Yeah. Okay. You will be defining your variables like this. These 3 registers and these 2 wires, and then you will create this test bench. If you need to, if you are trying to do this one, please try to get a screenshot of this example that I am showing on the screen right now. Please get a screenshot of this diagram, and then I will switch the screen to the code that we wrote just now. Then you will be using that code to modify and make this one. Okay, I hope you have screenshot this one. Yes, this is the code that we have just wrote. Now you can modify, you can leave this one here, right? You have to write a new line here. Your display commands will be a little bit bigger. This part will leave it as it is, and you will have some additional lines here. Please try to do. Okay, I just got the first successful answer. Okay, I'm going to give 1 minute for everyone, and then whoever this unknown guy SLW453, can you share your screen and show others? Okay. Only someone from the organizing committee, can someone from this audience share the screen?
Yeah, we have enabled screen share.
Okay. Can someone share the screen and show? Or even if you need to explain in any language, Sinhala or English, don't mind. If you can explain how you, what are the things that you just modified, can just share. Okay. Can anyone share? Okay. So I think I know few people have got the answer, but no one is going to share. So this is what one thing I got just now, a couple minutes back. Someone shared it with me. This is the screenshot. Okay, I hope you have got the idea, and so basically there are several ways of writing a code, and you will identify those methods. So this is not just the only way, and this is not just the only way of like introducing the AND gate. Even you don't need to introduce AND gate in Verilog. You have predefined AND gates available, but this is I just did one for the demonstration purpose. Even you can write complex Verilog codes here, complex codes here, so that will modify this circuit, and basically you can write multiple gates, multiple files. You can import multiple files to a single test bench, and then compile and simulate. So you can do a lot of things. The only difference is this is not just like a normal computer language. It describes a physical circuit. So starting from this point, once you have done your logic simulation correctly, then we will be able to move to the next process. That means I'm explaining the actual process that we are going through in EDA. So once you have finalized your logic, then you can do all the safety checkings and all the heat dissipation testings and all other testings, and do other designings, layouting, flow plannings, power estimations, clock domain crossings, and resolve all these questions. And then a final product will be a computer chip or mobile phone chip or something like that. So everything that you use uh, is coming as a product of EDA, that's for sure. So if you are using mobile phones, if you are using a Samsung mobile, then uh, that might be a uh, that might be a mobile phone that is using a ARM chip, or maybe a Qualcomm chip. or something like that. If you are using Apple mobile, then might definitely using Apple core chip inside CPU and GPUs, and everything is a product of EDA. Basically, that is the introduction of myself. So I am a application engineer in Synopsys, and Synopsys is a leading EDA software developer. So basically, what we do is we develop tools in EDA. So our customers are the customers that I just explained. So our customers are not like end customers like you. So we make the tool, and the manufacturers of these electronic chips, so anything, they uses our program, and they use our program, and then they will build their chips using our programs, and then they will manufacture mobile phones. So that is how the Synopsys comes into the EDA industry. Okay. Yes, that is the end of the session. I think you got something new. You can always browse internet for finding help. So there are a lot of resources available. Even for this one, before making this one, I just got a sample code from internet. So you don't need to worry about getting help. So there are a lot of resources available on the internet. So you can just give it a try. And yeah, that's all. Thank you for inviting me. And I think we have some quiz coming up, and I hand the session over back to the OC.
Thank you very much, sir. So that was undoubtedly a very informative session for everyone, and I'm quite sure that everyone in the audience learned a lot from it. So now, if you have any questions that you'd like to get answered, we are going to move into our Q&A session. So you can unmute yourselves and ask your questions from our guest speaker, or if not, you can send your questions to the Zoom chat so they can be answered. So please take this time to clear your doubts from today's sessions, and through that you will be able to gain more insights into what you've learned today. So please make use of this chance. Guys, so if you do have any questions, you can unmute yourself or simply put your question into the chat in Zoom.
Yes, I just few minutes back I got a question, so I'm going to give the answer here. So I think a couple of you are requesting this one. So the answer is for this value change, right? So you have experienced that 111, even though all three inputs are 1, the output has not yet turned to 0. Okay. So I am leaving it to you. So the reason is the output has not yet changed. Okay. So that is the reason. So you are trying to probe at the very beginning of that simulation. That means the display command runs at the very beginning, but the output hasn't changed. You can think it logically. I'm not going to say it, and try to figure out what is happening here. But if you like going to leave one time unit after that one, then you will see the proper time output, right? So you have to think logically there, why it is happening like this.
So seeing that those are the only questions that we've had during the Q&A session. We can move on to the next part of our day, and that is to take some time to show our gratitude to today's speaker. So Mr. Ruchira Pereira conducted a wonderful session, which was very interactive as well for us, and he took his time for it and made a great effort for it. So dear sir, please accept this token of appreciation from us.
Thank you very much.
Okay, thank you. So we can now move on to take a screenshot. So there's a virtual background provided in the chat. So if you're in a position to turn on your camera, please download the virtual background and let's take a quick screenshot. So yeah, we'll give a few seconds for everyone to get ready and turn on their cameras, and we'll move on to take a screenshot.
Okay, thank you.
Thank you so much, everyone. So now the next session part in our agenda for today is the quiz. So all our participants have been through most of the sessions with us, and by now you're quite familiar with the agenda and about how this works. So to put it briefly, what happens is we're going to have a 10-minute quiz, and the link for the quiz will be provided in the Zoom chat. So it's going to be a Google form. And once you have answered the question, you can submit your answers within 10 minutes. So please fill in the questions, because the marks for this quiz will count as the attendance for your session. And this is going to make you eligible for the ECC certificate that we are going to provide. And also the 3 top scorers for today's quiz will be receiving a valuable printed certificate. So please don't miss that opportunity either. So we will be posting the link for the quiz in the chat shortly. Okay, so the quiz, a link has been provided. The 10 minutes will be starting now. We have 2 more minutes remaining. We have 1 more minute left. So please make sure to submit the quiz as it will be considered for attendance. Please submit your quizzes now because the time is nearly over. Okay, the time is up. So we will give 1 more minute for you to submit your answers. So today has been a very interesting session where all the participants got to learn a lot of new things. So I would like to send a huge thank you out to the participants who joined the session. So this is the second, there are going to be 2 webinars for the second phase of SparkLink, and this is the first session for phase 2. So our second session for phase 2 will be on the 22nd, which is the next Sunday. So we hope to see you on that day as well. So throughout these days, you've been with us and you've joined into all the sessions. So please join with us onto our next session as well. So till then, good evening and have a great week. Thank you for joining.